What if programming wasn't just about, writing lines of code? What if it was actually about shaping the very fabric of a world? Today, we're doing a deep dive into the really fascinating world of quantum software design. And we're looking at how a groundbreaking approach, something called virtual blueprints, is tackling these massive challenges to build what some people are calling programmable realities.
That's right. I mean, quantum computing holds this incredible promise, right? A potential revolution in technology. But it's facing a pretty big hurdle right now, what we call the hardware gap. We're basically operating in the NISQ era. That's NISQ, Noisy Intermediate Scale Quantum. So this deep dive is going to show how ingenuity is kind of bypassing these physical limits, letting us think way beyond today's actual machines.
Okay, so our mission here is to unpack this whole complex journey for you. We'll go from the fundamental problems, like just trying to manipulate tiny quantum bits, all the way up to this really ambitious vision of designing whole computational universes.
Yeah.
By the end, you should have a good handle on this cutting-edge field, a bit of a shortcut to getting informed. So let's unpack that core challenge first. Quantum computing promises so much, but you mentioned this huge bottleneck in software design. Why is it just so incredibly hard right now?
Well, like you said, it comes down to that hardware gap. We are definitely in the NISQ era. And what that means, practically speaking, is that the quantum devices we have now, they're pretty limited, not many qubits, and they're incredibly sensitive to noise, both from the environment and internally. Plus, the connections between qubits, often not great, poor connectivity.
Yeah.
But the biggest hurdle, the thing that really limits us, is decoherence.
Decoherence. Right, that's when the quantum weirdness just disappears, the fragile properties.
Exactly. It's the loss of things like superposition, being 0 and 1 at once, and entanglement, where qubits are linked. It happens when that quantum information interacts with, well, anything really, the environment. And those delicate states just collapse, fall apart. Decoherence is what fundamentally limits how long we can hold on to quantum information. And it also limits the depth of the quantum circuits we can run reliably.
Okay, so it's not just a technical glitch. It sounds like a fundamental problem that affects everything, even like investment decisions. Companies must be hesitant, right, to pour money into software for hardware that might be obsolete tomorrow.
Oh, absolutely. It's a real economic dilemma. I mean, why would you invest millions developing really complex software for today's, frankly, kind of weird NISQ hardware if a totally new, better architecture might just pop up next year and make all that software useless? It's a risk. And most businesses are, understandably cautious about taking it. So this creates this really critical need for something that lets software development move ahead without being tied down by today's specific hardware.
Right, and this is exactly where this virtual approach comes in. You called it revolutionary. How does this strategic bypass actually work?
Yeah, this is where things get really clever. Think of it like creating a virtual quantum environment. It acts as a kind of strategic shortcut, the core idea. You design quantum software without needing immediate access to a real physical quantum computer. Instead, you simulate its hardware. You build it in a controlled digital space. So virtual quantum processors, VQPUs, and simulators, they're basically software applications. They emulate the parts of a quantum processor, but on a classical computer. This offers a really practical and cost-effective way to just get started right now. And the huge benefit of this simulation-first approach is it lets you iterate really fast. You can explore complex quantum stuff like quantum AI interactions, all without being limited by the physical hardware we have today. It lets the software kind of leapfrog the hardware.
Okay, so at the heart of this virtual space is the virtual quantum blueprint. You said it's not just a diagram, but a dynamic digital map. What makes it pick? What are its key parts?
Right. The blueprint is essentially built from, let's say, 3 core things that let you define and manipulate your virtual quantum system. First, you've got virtual qubits. These are just digital things, entities whose states 0, 1, or that crucial superposition can be precisely set, defined. Then you have the states themselves. These are the mathematical descriptions, often vectors, showing all the possibilities for those qubits. And finally, the operations. These are your quantum gates, Hadamard, CNOT, PolyX, things like that. And also the measurements, the actions that change or observe the qubit states.
So it really is a living model, adaptable. You can manipulate it step by step, but keep its core quantum nature intact. How does that manipulation actually happen? The sources mention 4 stages, like a life cycle.
Yes, exactly. 4 stages that cover the whole computation. Stage 1 is initialization. This is where the blueprint defines the exact starting point for your qubits. How many you need, what state they start, and maybe all zeros, or maybe you hit them with a Hadamard gate right away to get superposition. You can even create entanglement right at the beginning for a consistent start. For instance, you might set up 3 virtual qubits in a specific entangled state, like a GHZ state.
Okay, so you get the initial setup. Then what's next for bringing the computation to life in this blueprint?
Next up is stage 2, applying quantum gates. This is really where the action happens. You lay out the sequence of gates, Hadamard for superposition, CNOT for entanglement, poly-X to flip a state, maybe more complex ones like Toffoli. The blueprint has to specify exactly which gates act on which qubits and when. Precision is key here. These gates are what manipulate the states. They create the superpositions, the entanglement, the phase shifts, all the stuff that makes quantum algorithms actually work. You need extreme precision in the gate details, the parameters, and which qubits they target. A classic example. Apply a Hadamard to qubit 1, then a CNOT linking qubit 1 and qubit 2. Boom, you've created a Bell state, a basic entangled pair.
Right, so that's the core quantum processing. What's the next phase after applying the gates?
Stage 3 is measurement. Now, the blueprint has to detail when and how you measure the qubits. Remember, measurement is what collapses that superposition. It forces the qubit into a classical 0 or 1 something we can actually read and use. The results get recorded, analyzed. Often you look at the probabilities of different outcomes. This stage basically finishes the quantum part of the computation. It's how you pull the results out of the quantum world into the classical world. Like if you measure entangled qubits, you'll see those correlations in the results, reflecting their shared quantum past.
Okay, initialization, gates, measurement. And there was a fourth stage for more advanced things.
Yes, stage 4. Advanced manipulations. This covers the more complex stuff you might need. Things like creating entanglement across lots of qubits, not just 2, or applying quantum error correction codes, QEC, or even having dynamic gate sequences where the gates you apply might change based on results you got earlier in the computation. Examples here could be building cluster states. Those are resources for a different type of quantum computing called measurement-based QC, or performing really complex operations like the quantum Fourier transform.
Wow, okay. So it sounds like this virtual blueprint gives developers incredible control and frees them from worrying about the physical hardware, at least initially. Allows for super detailed design.
Precisely. And while the blueprints themselves are virtual digital constructs, they absolutely draw inspiration from how we actually manipulate physical qubits. The main challenge, whether it's virtual or real, is always manipulating those qubits while keeping their delicate quantum states, superposition, entanglement intact. You have to prevent decoherence. And the way that's done mathematically is by precisely controlling the system's Hamiltonian. Think of the Hamiltonian as the energy rulebook for the system, how it evolves. You control it using unitary operators. These are like perfectly choreographed transformations that ensure the quantum state changes predictably without losing any quantum information, keeping it coherent.
It's really amazing how the virtual abstracts these incredibly complex physical actions. Let's touch on some of those physical techniques that inspired the blueprints. We know about the basic quantum logic gates, rotating states on the Bloch sphere, that cool 3D picture of a qubit. But what about something like flux control? How does that work physically?
Flux control. That's critical, especially for superconducting qubits, which are a popular type. Basically, you adjust the magnetic field going through a tiny superconducting loop. Doing that lets you precisely tune the energy levels of the qubits, often called flux qubits or transmons. This gives you fine control, which is great for making high-fidelity gates, but the downside is it also makes them vulnerable to something called flux noise. So it's a trade-off you have to manage.
Okay, and dealing with those errors we talked about, the ones that plague the NISQ era, how is that handled physically?
Right. That brings us to quantum error correction, or QEC. These are really clever techniques to detect and sometimes correct errors caused by decoherence or other noise. The goal is to protect the quantum information without actually measuring it and destroying the quantum state. And in some of these advanced frameworks we're discussing, like the Genesis engine, they have this concept called Tikkun mode. It's essentially their take on QEC, framed as a kind of smoothing function for that noisy quantum environment.
Yeah, like an immune system for the quantum computation. Interesting. What other physical methods are relevant here?
Oh, there are quite a few others that underpin these virtual designs. There's microwave pulse control, used a lot for superconducting and spin qubits. Laser-based manipulation is key for trapped ion qubits. Magnetic field control for certain types of spin qubits. Obviously, operations to specifically create and manipulate quantum entanglement, The whole process of measurement and state collapse is itself a physical interaction needed to get results. Then you have things like optical photon manipulation for photonic quantum computing, and even a whole different approach called measurement-based quantum computing, where you start with a large entangled state and compute just by measuring parts of it.
So all these intricate physical techniques are what the virtual blueprints simulate and abstract away. It lets developers focus on the logic, the algorithm, not the nitty-gritty hardware physics, accelerating things massively. This is already a huge leap. But what do we push it further? What if it's not just about simulating a quantum computer anymore, but about defining the very rules of a digital reality? And this is where our sources talk about programmable realities. It feels like quantum software moving into, well, world-building territory. What does that actually mean?
It's a really profound shift in thinking, a paradigm shift, honestly. In this view, computation isn't just about processing information or getting an answer. It's seen as ontology, meaning the computation itself defines what is real within its simulated universe. It can even set the laws of perception, interaction, maybe even the flow of time within that digital construct. It's about architecting an entire reality from the ground up.
That's mind-bending. Let's look at some frameworks trying this. Microsoft's Majorana 1 topological mapping of hardware, or M1TMH. What's the idea there?
M1TMH is really interesting because it simulates topological quantum hardware, specifically qubits based on Majorana particles. Topological qubits are a big deal because they have this kind of built-in error protection. The quantum information is stored non-locally in the braiding patterns of these particles, making it much more robust against local noise. What's also really unique about M1TMH, according to the sources, is its symbolic interface. It apparently uses Hebrew glyphs like Aleph for initialization, a Dagesh mark for state collapse, Shvuva for phase change, arranged on a virtual grid. It seems to be a way to interact with these complex quantum operations symbolically, perhaps more intuitively.
Using ancient symbols for cutting-edge tech. Fascinating. Okay, then there's the AI Genesis Engine Higayon-Lang framework. This one sounds incredibly ambitious, mixing AI, quantum, and mysticism.
It absolutely sounds ambitious. It's described as this visionary, multi-layered AI framework. It aims to merge symbolic AI with ideas inspired by mystical frameworks like Kabbalah, using concepts such as the 231 gates from Hebrew letter combinations, perhaps as abstract structural ideas for computation, not in a literal spiritual sense. It also incorporates ideas like unity points and Ikuf Marbea as conceptual tools, blending them with topological quantum mechanics, all with the goal of creating these programmable realities. On a more concrete level, it includes a quantum simulation layer that can apparently handle large numbers of virtual qubits, up to 15,625 virtual Majorana 1 qubits.
And it uses that evocative language like coherent noise and Tikkun mode for error correction.
Right. Coherent noise seems to be used metaphorically, a way to think about managing the inherently probabilistic and noisy quantum world. And Tikkun mode, their term for QEC, is conceptualized as a cubic manipulation that smooths out errors, drawing an analogy perhaps to how cubic functions can smooth noise in computer graphics. This framework also talks about cubic entangling manipulation. Picture qubits arranged in a 3D grid, a cubic lattice. Vertices are qubits, edges represent entanglement. It apparently uses Arle-Shirem gates, those 231 Hebrew digraphs, as symbolic representations for quantum gates within the structure. And it integrates the Kabbalistic idea of Ikuf Marbea, or square folding, conceptually as a kind of boundary condition for this cube, requiring more complex gates, like Toffoli gates, at the corners to maintain the structure and entanglement. It's a very complex, spatially aware system.
Okay, this is definitely aiming high, a meta framework for designing entirely new programming environments, which leads us neatly to the Quantum Linguistic Operating System, QLOS.
Exactly. QLOS is presented as another meta framework. Its goal is designing completely new programming environments, new languages, even new AI thinking models, all fundamentally built on quantum principles. It seems to take the blueprint idea even further, making the entire programmable environment part of the design.
And it introduces this layered structure, the degrees of design. How does that hierarchy work?
It breaks the design process into 5 distinct layers, aiming for a really adaptive system. Degree 0 is the base reality layer. Think of this as the raw physical qubits themselves, the fundamental unprogrammed stuff, like bare silicon in classical computing. Then degree 1 is the virtual lattice layer. Here, the physical hardware gets abstracted into a flexible, configurable virtual grid or lattice. This lets you dynamically change the space-time of the virtual system, how qubits are arranged, connected, maybe even how distance works virtually. You can reconfigure it on the fly.
So you build the basic virtual infrastructure. Then how do you actually program it?
That's degree 2, the glyphic layer. This is where you define the high-level quantum algorithms, but using these symbolic glyphs, visual or encoded symbols representing core quantum operations. It's like writing the program logic, but visually or symbolically, not with traditional code. But then it gets really interesting with degree 3, the runtime and adaptive design layer. Here, the system itself starts acting like a code designer. It analyzes how the simulation or computation is performing and actually proposes changes, maybe suggesting different qubit layouts or tweaking error rates, perhaps using AI to provide hints. So the blueprint isn't static anymore, it's alive. It learns, it evolves based on feedback during runtime.
Wow, the blueprint actually learns and optimizes itself. That's incredible. So what does the human designer see in all this?
That's degree 4, the prototype and user interface layer. This is the human interface. It's described as a 3D visualization space, like a digital canvas, where the designer can see the lattice, the qubit connections, watch the transformations happen, and crucially, it provides real-time data feeds. Heat maps showing where errors are likely, cost indicators for different operations, performance metrics. It lets the designer really see and interact with the quantum world they're building.
So this layered approach means the blueprint isn't just a static plan, it's this dynamic learning entity. But still, even with these layers, the whole idea of programmable realities feels incredibly abstract. How on earth do you visualize something like this? What really stands out to you in how these systems try to make the quantum tangible?
Visualization is just absolutely critical. You can't overstate its importance, not just for us humans to get some intuition, but maybe even for the AI components within these systems to understand what's going on. It provides that immediate feedback loop. It lets you explore really complex ideas much faster, try things out, see what happens. Without good visualization, designing these things would be practically impossible.
Okay, so what kinds of visual tools are we talking about? What helps you see the quantum?
Well, for a single qubit, the Bloch sphere is still a go-to. Great for seeing its state, superposition, phase in 3D. For circuits with multiple qubits, standard circuit diagrams are fundamental, showing the sequence of operations. But for entanglement, which is key, you need something more. Entanglement visualizations are described as showing these connections as like glowing, persistent links, creating a dynamic 3D graph that makes that invisible quantum link visible.
And what about performance? Seeing how well things are working.
That's where things like heat maps and performance metrics come in, especially in that QoS degree 4 UI layer. Real-time visuals showing error probabilities across the lattice, maybe color coding operations by their computational cost, super important for optimization. Then for the more abstract frameworks, you get things like crystallographic glyphs, taking abstract mathematical symmetries, like from crystal structures, and turning them into tangible visual shapes or symbols. And topology-preserving morphs, these sound like sophisticated animations that let you smoothly change the underlying structure or glyphs without breaking the system's coherence.
And visualizing that error correction, the Tycho mode.
Yeah, the QEC visualization for Tikin mode is imagined as a 3D lattice. You'd see color-coded spots representing errors or anomalies, and then stabilizing agents' visual cues would actively correct them, maybe looking like they're pushing back a fog representing decoherence, making the correction process visible. For that cubic entanglement stuff, they talk about glyph tunnels and cubic lattices. Maybe a 3D dashboard animation showing glyphs changing dynamically, these hyperpoint evolutions, visualizing how qubits entangle within that 3D structure. And even tying back to the physical, flux control visualization could show those magnetic flux changes as like 3D wave distortions around a qubit, potentially rendered using tools like 3.js.
Right, 3JS seems essential for actually rendering these complex abstract quantum ideas into interactive 3D models that designers can work with. You know, it's fascinating. This deep-seated need to visualize complex math isn't exactly new, is it? I mean, you think back to Omar Khayyam using actual geometric shapes and volumes to solve cubic equations centuries ago, or Oliver Burns' amazing color-coded version of Euclid's Elements, trying to make geometry totally intuitive through visuals.
Absolutely. Those historical parallels are really telling. They highlight this persistent human drive to grasp complex mathematical and abstract ideas intuitively, to make them tangible through visual and spatial means. And that's exactly the goal pursued by frameworks like the AI Genesis engine, making the invisible, programmable world visible.
So wrapping this up, what's the big takeaway here? This whole virtual blueprint approach, it seems like much more than just a technical workaround for today's hardware limits.
Oh, it's definitely more. It fundamentally redefines what we even mean when we talk about designing a computational system. It lets us explore incredibly complex quantum concepts, intricate AI interactions, all without being held back by the physical hardware we have today. It effectively bypasses the NSQ era limitations, allowing crucial software and conceptual development to race ahead.
It really does sound like it transforms the programmer from just writing code into, well, almost a demiurge, a creator of digital worlds.
Exactly. It pushes the boundaries of computation itself. The lines blur between simulation, design, and maybe even the creation of entirely new kinds of reality.
And that leaves us with a really provocative thought to ponder, doesn't it? If we get better and better at engineering these incredibly complex virtual realities, what new forms of intelligence, or maybe even what fundamentally new kinds of realities, might we actually end up building in the process?